Okay, so back earlier in chapter 13, we learned how to describe the sample space of a chance um, behavior. Another way to model that would be with a tree diagram, although a tree diagram is usually like a sequence of outcomes in an event. So not just flipping a coin once, but more than once. So something like flipping a coin twice and listing the probabilities of getting heads would look like that as a sample space. As a tree diagram would look like the following. Okay, so every time you branch off to its different probabilities. So initially it's half heads, tails, and then off of each one of those is heads, tails. So then how you can now read this is the probability that the first coin toss will be a half, and the second coin toss will be a half, would be half times 1/2, okay? The probability that the first would be tails times, and then the second one be heads would be 1/2 times 1/2, okay? Generally speaking, though, this is pretty much too simple for us, so we'll be looking at problems that are a little bit more complex than this. So this would be a good problem. So tennis great Roger Federer, he made 63% of his first serves in the 2011 season. When Federer made his first serve, he won 78% of the points. When Federer missed his first serve and had to serve again, he won only 57% of the points. So suppose we randomly choose a point on which Federer served. So what we first want to do is make a tree diagram of what this is suggesting, and then we'll find a probability that he makes the first serve and wins the point. First, let's take a look at what the tree diagram would look like. Wrong one. Okay. So the first choice is the first stem off is whether he's making the first serve or not. So makes first serve, misses first serve. Okay. The probability that he's going to make the first serve is 0.63. The probability that he's going to miss the first serve would be 0.37. Okay. They tell you that when he made his first serve, he won 78% of the points. So after he makes the first serve, he's either going to win the point or lose the point. Okay, 78% of the time when he won it. When he made the first serve, he won it. That means that 22% of the time he's going to lose it. They go on to tell you when he misses his first serve, he had to try to. He missed his first serve. He had to serve again, and then this time he only won 57% of the points. So 43% of the time he lost that point. Okay, so now we have a bunch of probabilities that can be read. So kind of like how I was working through the heads tails flip, right? So if he makes his first serve and wins a point, what's the probability of that, right? So the probability that he makes the first serve and wins the point. Now you're looking at the 0.63, follow along that he won, so 0.63 times the 0.78 means that there's a probability that this will occur will be 0.4914, right? Or I can say what's the probability that he misses the first serve and wins the point. Now you're going to follow this.
Now you're going to follow down below. So the probability that he misses the first times the probability that he'll then win the point. So misses the first times probability that he wins the point, 0.2109. Okay. And back to PowerPoint.
Okay, so let's take a look at another tree diagram. This tree diagram now will show conditional probability. So video sharing sites led by YouTube or popular destinations on the internet. Let's look only at adult internet users aged 18 and over. About 27% of adult internet users are 18 to 29 years old. Another 45% are 30 to 49, and the remaining 28% are 50 and over. The Pew Internet and American Life Project finds that 70% of internet users are aged 18 to 29 have visited a video sharing site, along with 51% of those aged 30 to 49 and 26% of those aged 50 or older. Suppose we select select an adult internet user at random. So the first thing that we're going to do is show a tree diagram, and then we'll find some probabilities, with that last one being a conditional probability. So given that this person, so that's how we know it's conditional. So it's easier for me to write on this program. Okay, here it is. Okay, so we have kind of three age groups, right, that it's starting with, right? So there's a 27% of users are 18 to 29. 45% of users are 30 to 49 years old, and 28% are 50 and over. Okay, so of the 18 to 29 group, if they are internet users, then 70% of the internet users have visited a video sharing site. So visits video sharing. So that means 30% doesn't. Kind of a lot to write, so I'm going to leave it at that. Okay. Of the 30 to 49-year-old group, 26 of them did. No, 51% of those. Let's jump into the 50 and up. So 51% of those visit, and 49% do not. And the 50 plus, we had, that was 26 visit, 74% do not. Okay, so now I can find some probabilities here. So if I first ask you for the probability that this person has visited a video sharing site, okay? So let's find the probability that they visit video sharing site. Okay, so that's going to be these people, but you have to trace them back, right? So 70% of the 18 to 29-year-olds, and it was 27% that was making up that group. So you have 0.27 times the 0.70, okay? Plus you had the other group, so you had the 51% of the 30 to 49-year-olds who were accounted for 45%. 51. And then last, the 50 and up, so you had 26% of them, and they accounted for 28%.
So 0.9. So the probability that they visit video sharing groups is 3, which is about 49%. And now let's find a conditional probability, okay? So we want to find a conditional probability that says, what's the probability that they are 18 to 29 given that they visit video sharing sites, okay? So what we're going to do here is put the probability that they're 18 to 29 and visit over that given, right? The given that they visit. That's always the denominator, whatever the given condition is in the probability. And the top for a conditional probability is always the probability of both happening, okay? So the probability that they're 18 to 29 and visit, right? So that's that kind of top level there, right? So they are 18 to 29 who visit, which we kind of already did in the previous question, 27 times 70% over the probability that they visit video sharing, okay? And the probability that they visit video sharing was what we were asked in part B, where we had to find out each one, okay? And so that goes there. And so the probability that they are 18 to 29, given that they visit video sharing sites, is 0.3847. So given that the person visits video sharing sites, there is about 38.5% chance that he or she is aged 18 to 29. Okay, one more example for tree diagrams. So one of the most important applications of tree diagrams and conditional probabilities is in the area of drug and disease testing. Okay, so let's take a look at PowerPoint and one more question. Okay, so many women choose to have an annual mammogram to screen for breast cancer after age 40. A mammogram isn't foolproof. Sometimes the test suggests that a woman has breast cancer when she doesn't really. That's known as a false positive. Other times the test says that a woman doesn't have breast cancer when she actually does, which is a false negative. Suppose that we know the following information about breast cancer and mammograms in a particular region. So 1% of the women aged 40 or over in this region have breast cancer. For women who have breast cancer, the probability of a negative mammogram is 0.03. For women who don't have breast cancer, the probability of a positive mammogram is 0.06. Here's our problem. A randomly selected woman aged 40 or over from this region tests positive for breast cancer in a mammogram. Let's find the probability that she actually has breast cancer. Okay. So let me see if I can minimize this. Nope. Okay, so see if I can drop this slide so I have what I need to work with here. Here it is. Okay, so here's the problem that I just had up. So the first thing I'm going to do is put up a tree diagram that goes with this, okay? So kind of where the branches start off is has breast cancer or doesn't have breast cancer, okay? So 1% of the women aged 40 or over have breast cancer. And that would mean 99% do not have breast cancer. Okay? It then says for women who have breast cancer, the probability of a negative mammogram is 0.03. Okay? So a positive mammogram versus a negative mammogram. So 0.97 that it's positive, 0.03 that it's a negative. Okay? And then if they don't have breast cancer, it came up that a positive mammogram was 0.06. So then, of course, the negative mammogram would have been 0.94. Okay. So now we need to find the probability that she actually has breast cancer. Test positive that she actually has breast cancer. Okay, so we're looking for the probability that she has breast cancer, given that it was a positive mammogram. Okay. So, as always, in a conditional probability, the top is going to be both of them. So the probability that the woman has breast cancer and a positive mammogram, so that's going to be kind of multiplying that top level there. Okay, and then we always put it over the probability of the condition. So the condition is that it's a positive mammogram. Okay, which is going to be looking at the all the positives and seeing what that ends up to be, or that positive top and then the top of the bottom. Okay, so the probability that they have breast cancer and is positive, so that's kind of that top row, right? The 0.01 times the 0.97, right? So I got 0.01 times 0.97. Okay. Over the probability that it was a positive mammogram. So the positive mammogram is going to be the combination of both tops there. So the one that we just did, and then positive when they don't. So I got 0.01 they have, and it was positive, and plus the probability that they don't have, which was 0.99, times the probability that it was positive, which was 0.06, okay, which is going to give me 0.0691. Okay, so ultimately this comes down to being about 0.14. So we would say that given that a randomly selected woman from the region has a positive mammogram, there is only about a 14% chance that she actually does have breast cancer. Okay. And that's the end of this video.